Live now?
Hi. Yep, we're live. Hi, Tekchun. Great to see you again. How are you doing?
Hi, Joey. Nice to see you again. Good, doing good. Yeah, hope you're doing well.
Yeah, I'm doing well. Thanks for asking. So,
Okay.
hi, folks, and welcome to the Google Developer Space channel. We hope everyone is doing well and keeping safe. If you're online now, do give us a shout out on the live chat or comment section to let us know where are you tuning in from. Before I begin, let me briefly introduce what we do and who we are. Google Developer Space is a platform for developers and startups from around the region to learn, connect, engage, and be inspired. And as part of the developer relations team, we aim to empower and connect the community to our people, program, network, and technologies, be it online like tonight or in person. Today, we're welcoming back Go Singapore, led by Tekchun over here. So without further ado, over to you, Tekchun.
Thank you. Thank you, Joey. Hello, guys. Nice to see you again. Hope everyone is putting up well. And thank you for tuning in this Wednesday evening. Today we have two speakers, and the theme for today's talk is around generics. We have the first speaker, Christopher from Shopee. He will show us how to do some templating to implement Go generics. And we have Bill. And Bill is a very familiar face in the Go circuit. Many people will know him. So he's tuning in from America. 12 hours time difference. Thanks to him for attending this talk and giving us his insights into generics. So without further ado, keep those comments coming into the YouTube channel, and we'll watch out for the questions as we come. Right? I hope you enjoy today's talk. So let's introduce Christopher.
Is that start now? Okay. Can you hear me? I don't know whether the presentation is done now.
Hi, Chris. Yes, we can hear you and we can see the slides. So the stage is yours.
Oh, okay. I will start. Hi all. Thank you for listening my presentation. I'm going to share my project, Better Go with you, which purpose is to make Golang great again. And here is something about me. I have been a wide contributor when I am in university. Though I am writing Golang in my job now for Shopee, but I am a big fan of Elisha. I use it in my last company, Alibaba Games, and I use it to write game middleware for Tapikaeru Chinese version of Alibaba and 618 games for Taobao. It is a small games platform. Okay, let's start. And here is the things I want to talk. People didn't really distinguish problem and solution. So I will explain what's my problem and why am I doing this in the presentation. There are 6 parts in my speech. The first thing is why we need this project. And is there anything we can use? Why we need ours? And the fourth part is how to do this. There are many methods can do the generic and dive into the method I choose. The last part is FAQ. So the first part is why we need. How do you remove an element in integer slice? And here is a method. It is the fast one. The order is not important. And if you want to remove an element in string slice, you will write another code. It is almost the same as the last one. If we want to write a generic remove function in Go, the first method we will use is to use an anti interface. And this one is the interface version. Delete a element in a slice. This one is good. You can use it in many versions, but it is slow. One of the co-authors of Golang, Rob Pike, had tried this method too, but at last he gave up. You can see his comments in README. He wants to see how hard it is to implement this sort of thing in Go. With a nice API, he could manage.
Hey Chris,
It is not hard.
sorry for interrupting. Actually your slides are not moving. Oh, okay, it's moving now.
Oh, this is moving, right? It's okay, right?
Yep, it's
Yes.
perfectly.
Yeah, one of the co-author of Golang, Rob Pike, had tried this. You can see the GitHub page. It is still there. Almost 500 stars. And at last he gave up, and he also said that you shouldn't use this version. It is slow. He had to try writing reduce and map. Since only reduce. So what is another method to write generic? It is Win. Win is the best way to write generic in Go 1. You can see this GIF. Yeah, this is one version to write generic. So that's why we need generic. You may not need in your business code in CURD, but basic library needs it.
So sorry. Actually, I think there's something wrong with the sharing. Would you mind sharing your screen again? So like just close it and let me.
Is it okay now?
Can you like move back and forth so we can make sure that it's working properly?
Is it okay?
Yeah, it's not moving somehow.
Maybe the GIF is too big.
So it's supposed to be showing the GIF, is it?
Yeah, the GIF. Can you see the GIF now?
Oh, okay.
Yeah.
I think it's very good. So I think let's just go ahead first and we'll see.
Yeah, I will wait this finish and change to the next part. Yeah, I think it's done. Okay. So that's why we need generic. You may not need in your business code in CURD, but some basic library needs that. For example, map, reduce, flat, zip, any, all these functions, and something in slice, find, delete, mask, minimum, and group by. There are many library functions which is less in Golang now because no generic. And when I write this project, I'm not sure when Go to generic arrive and can be used in production. So is there anything we can use? Maybe we can copy and paste from GitHub or Stack Overflow. At that time, I cannot find one suitable tool at that time. And I only found another language, Go Plus. It is another Go grammar. And it is compatible with Go language, but he needs to write his interpreter and his compile tools. It needs long-term and full support for IDE and Go build tools, etc.
Hi, Chris. Sorry to interrupt again. I think there's something wrong with the screen share. Do you mind stopping the share and then you can try to reshare again? For those tuning in, sorry about that. Please give us a few minutes to set up again.
Okay. Let me Let me try again.
Alright. Can you try changing your slides again, Chris?
Yeah, just change to another slide.
Yeah. Can you just try moving it a few more? Let's see. Are you changing it? Because we are at cannot
Okay.
find one at a time. Now
Yeah,
try inventing the view.
I know the trick now. I can change it and to make sure that it has changed.
Okay, Ken. Thank you so much.
Okay. So let me start from anything we can use. So I cannot find one tool at that time to do the things I want. And I only found another language named Go+. It is a static type language and compatible with Golang. And it is also secret-like. You can use an interpreter to use that language and use a compiler to compile it to Golang like binary. But I don't want this type of tools, and I don't, because it needs long-term support, and it needs to do something for the IDE different, because it has different grammar for, and it needs you to write another build tool. And it also requires you that has many influence, so you can convince people you use this. So I decided to invent the tool. My target is that the tool is compatible with Go grammar and with high performance and rich library functions. And how to develop this? Monopolization. It means generating specification versions of generic functions. For example, like C++ template. If you had used C++, you must use C++ template for some kind of functions like stack data structures, cube data structures, vector, etc. And this code is a usage of template. For those who don't familiar with C++, you can see the base integer of get mass. It is a specific type integer and long, and it will replace the T type and generate a specific version of get mass. For example, integer get mass and long version get mass. So that's what I want to do in Golang. Implement it, and this is code generation, because we don't want to change Golang's grammar and compile tool. C++ will not generate the code, but will generate a section for function. It is in the binary, but it doesn't matter. So for the users who use this tool, I want to provide a anti-interface version for them, so that they can use it in their code without any changes. And it can use our tool to generate the specific version function for them. And I will also replace his original call in the code. And he can directly compile it and release the binary. That one without specific function and no interface. So let's get into it. Doing this is like put an elephant into a refrigerator. The only thing we just need to do is that write interface version functions and you do the code generation for specific function. And you can see how this is implemented. This is a pull request of making a map function. And the right part is writing an interface version of map. You can see this reflect the get the type of slice and get the type of the function and reduce it and map the function with every element and change it. This is the interface version and package provide to the user. User can directly use it in their code and comply, and everything works well, except the performance cost. And to implement the function like this, you need to also write a generic template. Here is the map template. I will record the parameters as argument name 1 and argument name 2. In the map, grammar, the first argument is the slice. The second argument is the function. The function used in the slice every element. So here is how to use it. I just got the length of every of the slice and use the function argument name 2 to every argument I. So this is the specific version of the code. I will generate a code like this, and behind is the specific parameters of the function. I will record it in another code. When I look the user's code file, I will record how many functions are there, how many parameters are there, and record them so that when you generate the code, I can know all the variable types. I will dig into this later. You can see here, this is a function declaration. I will remember the function name, parameters, type declaration, and the function body. The function body is generated in here. Okay, I will explain them later. And this is how a user use this tool, and they can just use the interface version in their code, and everything works well. Like here, the file function is the interface version, and people can use it directly and comply and test everything works well. And then he can use our tool to do the code generation for specific work function, and then release the binary. And here is the example I made to use this tool. For example, this is a user how to use our tool. For example, this is the package I provided. So you can use it like this and this. And after finish the code and everything works well, you can just install our tool, our binary, and then use it to select the file to generate. So after this, I will generate a specific version in this directory. I will show you later. And at last, it can directly comply. Yeah, this is how this. Here's something about how I do it. At first, I will look every file in the user's code and analyze it using the package AST, Golan's AST package. AST can analyze each element. For example, there are basic declaration like import constant declaration, variable declaration, type declaration, and assignment statement, function declaration, type assertion expression, call expression. And I can according to the function declaration and call expression to know the user is using the enumerable package, using my package, so that I can, according this package, to record all the variables and types, and then generate a specific function for them. For example, this is the AST operation. You can see I just make sure that this expression is a function called expression, and I get its name, its function name, and I to judge that whether its function name contains my keyword in new. And then I will get its function declaration, like the new function name, function declaration string. I will generate this for them, and then I will rewrite them and replace the original call. And I will stop sharing my screen and sharing my item. I will share how to do this from an example. Wait a minute. There's a bug. I cannot share my item. Yeah. Oh. Sorry, since I cannot share my item, so I will just share the code. So I will just share the GitHub's code for you. I cannot use my item in this presentation. So this is how a user input their files, and I will use to replace them. And then after the file is not empty, I will load this file and to rewrite and generate the function for them. Load the file is load the AST's every node. AST is a tree. I will loop every node. And according to the loop, I can decide every type. Like this is the general call. This is the usually value. This is a assignment, like a equal to 12. This is a function declaration. This is type expression. This is a function call expression. And here is that I found that the user is using our package. I will generate a code to them. And this one, I will decide which function he is using. For example, we now has reduce, add, map, delete, and find functions. And in this function, I will extract the function's parameters and list of arguments. For example, basically is the basic expression. Function list is a function expression. And ident is the argument declaration, so that I can record every function type, argument type, and variable types, so that I can reuse these types, reuse this to generate a parameter type declaration in the function, and compose them into a function call. That's all. And I don't know how to share my items, so I cannot show the results and how can you generate it to you. But there are the dots in the GitHub page showing how can I do this. So let's return to the AST, and that's all. Thank you. You can ask me questions. And here is the Better Ghost GitHub project. And if you are interested, you can join the Telegram group. Its name is Better Go. Thank you.
All right, thank you, Chris. Thank you.
Thank you.
I'm watching the feed to see if there's any questions. No, I don't see any. Yeah.
Okay.
So, in any case, feel free to post questions even after it's stopped. So thank you, Chris, for the sharing. We will share the link later. And next up, we have Bill. We'll talk about generics proposal in Go2. Right. Over to you, Bill.
Can hear me and see me. I'm going to switch this browser over here so we don't get a bunch of fun visual stuff. All right, my name's Bill Kennedy, and I really appreciate everybody being around. Just be aware that I can't see anybody. I can't really see your comments. So what we're going to be doing for the next hour is I'm going to try to show and teach the current draft syntax for generics. And when I'm done with this, I'm going to try to do this in about an hour. And when I'm done, then I'll take those questions. And I'm really hoping that throughout the next hour, you're all actively chatting and talking about what I'm showing. My other goal here is not just to show you the syntax so you can get a feel for it. Many of us are working. Many of us don't have time to directly work and play with this. But I also want you to get a sense of, does the syntax still feel like Go? And I'm going to inject some of my own personal opinions as we go. Now, I've asked the organizers to drop 3 links into your chat windows. The first link is to this page right here, which is the GitHub repo I have for all of the generics code that I've written to date for training. And you see like 11 different examples here. We're only going to have time to look at the first 7. So I'm marking my clock here at almost 7:30. By 8:30, I will stop and we'll be looking stop with the code review. But then I want you to take your own time to look at everything else that's in here. So my goal is over the next hour to get through items 1 through 7 and show you that syntax. Now, in the README on this GitHub repo, you're going to see a link over here. That is to the draft document. I've also had the organizers drop a link to this document as well. And this is what I'm going to be trying to share as much of what this document is providing in code. There's also a Go playground link here in the README. And this gives you an opportunity to play with the syntax on your own. I won't be using the playground links. I will be running everything locally, and I'll show you how you can do that as well. Now, I've stolen a couple of items from the draft document, this very high level overview, which I will not be reading. is what is currently slated to be part of this first release of generics. Everybody asks me, when is generics going to make it out? Well, it's got to be right, but I think the goal is for maybe August, the August release of next year. So maybe around August 2021, maybe the release after that in 22. It all depends on you really getting involved and helping flesh out all of these remaining issues that we have. When I say issues, I mean just conversations we have to have on syntax so we get it right. I'll talk more about that at the end. But this is what is being looked at right now for first release of generics. And then I've gotten omissions, which I stole out of the draft document as well, which is currently not being worked on. It doesn't mean that this stuff may not make it in the language over years to come. It might not even come into the first release, but currently this is not slated right now, and it's not implemented. All right, but if there's a need, it will happen. This document, it's a living document, so we're gonna try to do our best to put in the bare minimum that's needed for the first release of generics, where there's real value in having it. And I'm gonna try to share some of that with you as well. Now, I'm gonna be running everything locally on my machine, so the README also walks you through checking out the source code for Go, then checking into the branch for dev go, and then building everything. And as you'll see right here, if I do a Go version call, I'm not running 1.14 or 1.15 beta. Here I am. I'm running a version of Go from source back 5 days ago. Now, one last thing I want to stress here before we get going. What I'm going to be running is a transpiler, all right? Generics has not been at any level actually implemented into the language just yet. We're still learning and trying to work through the syntax issues. So what has been currently implemented is a transpiler, and we're going to be writing code with the new generics syntax, but the transpiler is going to be converting that into code that Go can build and compile today, and then I'll run it. And I just want to stress this out, that it hasn't been implemented yet at all. There's lots of other decisions that have to be made once the syntax is in place. So we're really just going to focus on syntax choices right now, and everything is open, all right? At least for those things that we can do. So I'm going to jump right into it. It's a 7:33 on my clock. I want to finish at 8:33 and then have time for those questions. So let's jump in. Again, I want to stress one more time. My goal here is to teach you the syntax that's currently available in the draft. For many of us, we don't have time to look at this, and I want as many people in the community to have an opportunity to see it and to share their thoughts and opinions and help form where this ends up in a year. All right, so let's get going. Now let's say I wanted to write some print functions that could take a slice, maybe in this case, line 13, a slice of integers, and I want to range over those integers and display the value of each int. Well, here it is on line 13. I've written a function called print numbers. It takes a slice of int, as you see, and within the scope of 5 lines of code, I'm going to be able to range over and display those integers. Now, I'm going to make an argument here that I think Go developers of just about every level, even if you've only been coding in the language for a couple weeks, can read and consume this code and maintain this code, right? We all can look at these 5 lines of code, and I think we can all figure out what's happening. If you've never seen the for range before, you can see it's a linear traversal. Okay, great. Now, if I wanted to do the same exact thing with a slice of strings, what do I have to do? Well, at this point, I could go ahead and I can write another function called print strings. It now takes a slice of string, there it is, and I can take the same 5 lines of code and reuse them here and maybe change some variables around. But these 5 lines of code will print strings as much as the other 5 lines of code will print those numbers. All right. And if I now want to do this with floats, I got to write another function, right? There we go. I go, Bill, write another function, write another function. Okay, so we can do this. I can write these functions. They're they're going to be maintainable by most Go developers, and that's got to be a goal at the end of the day, right? The readability and maintainability of our code has to be a goal. It's so important. And so I could add that next print float function, and we can all maintain it. But I know what you're thinking. Bill, what are we going to do, write 20 of these functions? Well, so if you don't want to write 20 of these functions for 20 different types, let's think about it. Is it possible to write a single function today in Go 1.14? Is it possible to write a single print function that could, at least at this point, print both that slice of int and slice of string? Well, there actually is. Here's a function called print assert, and it's using type assertions in the language to do just that, a single function to print both that slice of int and string. Now, if you look in the print assert function here, we have the use of the empty interface. It's how we're able to accept data of any type. And in this particular case, what we care about are slices of ints and strings. So we use the empty interface to accept the data of any type. And then we perform that type assertion here on line 37. And then we can ask the question, was the data a slice of int or a slice of string? And then we can perform those linear traversals with variables that potentially make more sense. Now, in this particular case, right, this print assert function, it's working, but really hasn't solved the full problem. I mean, all we've really done is taken 2 functions that I wrote and we've moved them into case statements, didn't we? I mean, if I want to now print a slice of float, I have to write another case statement. It's all I've done is kind of consolidated the n number of functions I would have had to write inside of a single function. Now, the real idea here is, can I write a single function that can print that slice of int and string and even float without having to write any more code? Can I write a generic function in Go? And the answer is yes. I mean, I'm going to make an argument that Go really already has generics. 1.14 already has generics. Now, how can I write a generic function in Go to print out the values of any slice? Well, here we are. Here is my print reflect function, and it's using the empty interface again. That's how we're going to accept that data in a generic way. And by leveraging the reflect package here, I can display the values of any slice without having to write any more code. Now, if we look at this code, right, we're talking about what? 3, 4, 5, 6, 7, 8, 9, about 10 lines of code. We've doubled the amount of code we needed from our concrete versions to do this. But you can see here I can reflect on the concrete data stored inside of the variable v. I can validate if it's a slice because I can accept any type of data. We have to do this validation. Now, if it's not a slice, it kind of breaks the semantics that we had before. I may have to do some error handling here, but minus that for a second, I can, not using a for range, but iterating over with I can iterate over the slice and then using this interface method, get to the value and I can display it. Now, I'm not going to make the argument that Go developers of all levels can consume this code. I mean, let's get real. You have to understand how the reflect package works. And even I had to look up the documentation to write this. So we're losing some level of readability and maintainability here as it relates to, everybody here on my team. But I did write a generic function. There it is. Okay. And, one of the things that I've been kind of leveraging in all 3 solutions is the fact that the print function uses reflection as well. I mean, I could argue that the print function is a generic function because it can print a value of any type. I was leveraging that in the other implementations to keep the code as similar as it was. But here we are, we've got a generic function nonetheless. Now, the question that I ask myself is there value in being able to write a generic version of this print function without the added complexity of the reflect package? Now, I love the reflect package. I am not talking down on it when it comes to marshalling and unmarshalling and data validation. The reflect package is awesome, and I am a big fan, okay? But as I am showing you here, in certain cases, right, like this, we're walking away from some level of readability, and we have to learn that package API. So I go back to our original concrete functions, and I ask, is there value in being able to write code like this, 5 lines of code, where it shouldn't matter if that's a slice of int and string? And I think in many cases, this could be really, really valuable to simplifying some of the code that we want to write today. So the question is, can we leverage this implementation and do it in a generic way? Well, we can't do that right now in 1.14 or even the release of 1.15 that's coming out. If we want to write generic functions, this is where we're at today. But with the new generic syntax, this is something now that we could solve, and we will be able to solve when generics comes in. So I'm going to show you the generic version of my print function. And before I break it down, before I do that, I want you to look that I'm using the same 5 lines of code that I used in the original concrete implementation. One of the beautiful things about the generics here is that we're going to write code as if we're working with that concrete type that we want. We write code with the idea we're working with the concrete type, and we can eliminate some of the added complexity of reflection. Now, this is our first time looking at this, and I want to break this down and get an understanding of why we need some new syntax anyway. And I'm going to do this throughout the presentation. I'm just going to get rid of some code here. And I want to just start right here. Now, on the surface, this print generic function that I've provided, right? You all know what I'm trying to say here. Hey, compiler, I would like to work with a slice of some type T, okay? Not necessarily an int, not necessarily a string, but some type T, please. And then from that slice of some type T, can we go ahead and perform that linear traversal? And thanks to print already being a generic function through the use of reflection, can we just display a value, each value of that slice of some type T? I mean, this is what we want to do. And it would almost really be beautiful if this is all we had to do. Just say some slice T. But that's not going to work, right? Because in this form of the code that I've written, the compiler at this point expects T to be defined by us. At this point, the compiler expects that the programmer has done something like this before we try to compile or build the program. The compiler expects T to be defined. Now, the point here is I don't want to define T. I want the compiler or at compile time for T to be defined, right? At this point, the compiler is expecting T to be defined before I compile, but I want the opposite. I want this to be defined at compile time. And so we kind of get stuck in a dilemma here because we now need some extra syntax to tell the compiler that, hey, I ain't defining T. Don't go looking for it. It ain't going to exist. We need to identify what T is at compile time. Now, there's lots of ideas and thoughts out there on how to give the compiler that information. But at this point in the draft, the current leading idea is to use a square bracket, use the keyword type, and then create a list of identifiers which will represent these generic types to be determined at compile time. And so I've put back the square brackets between the function name and the parameter list. And what we're doing here now is telling the compiler, hey, don't expect me to define T. It's actually up to you to figure out what T is, or I will explicitly tell you what T is at compile time. Now, the original draft did and still does allow for the use of parentheses here to define this type list. But I feel that the square brackets are easier to use and to read. And so I'm going to stick with the use of the square brackets. Now, just to get this out of the way here, lots of people want to use this syntax, right? This is traditional syntax coming from Java and C++. All I'm going to say right now is that using the angle brackets is just not feasible in Go because of backwards compatibility issues with the language, and we are not going to do anything to break backwards compatibility. So it's just not feasible. If you want to know exactly why, get to the ardenlabs.com website and look at my latest blog on these examples. And at the bottom, I explain very clearly why angle brackets are just not feasible. I'm not going to take the time to do that now. I just want to get that conversation over with if that's what you're chatting. It's just not feasible. Now, the square brackets, you know, Go is not setting a precedent. There are other languages out there. I think Scala is one of them. The programming language D is one of them. I think that are using square brackets. So I think it's a good choice. But if you got better ideas, definitely jump out there and express those. Now, we now understand the need for this list of generic type identifiers, right? The whole idea is to tell the compiler that don't expect me to define T before I hit compile. We're going to have to identify what T is at compile time. But because of that, I'm able to write code here as if T is a concrete type, and I get to simplify the implementation of this print function. Again, I know I'm leveraging some of the generic goodness of the print function to do that, and I will continue throughout this talk. Now let's get a sense of how this code runs. And I need to stress again right now that what we're going to be using is a transpiler. This hasn't been really implemented in the language yet. So we're not really sure, and the language team isn't 100% sure if what they're going to do is generate unique versions of this function for every given type T that is used. They might actually leverage generics underneath, and there may still just be one function to rule them all. These things have not been decided. So if you're already asking questions about, will generics provide better performance in some cases, the answer is, I don't know, because we don't really know what the implementation is going to be yet. Right now, all we're doing as a community is focusing on the syntax choices. So let's just stay there for now. All right. So here's the main function here. And one of the things I wanted us to get across was as I construct that slice of int and construct that slice of string, I'm able to pass that slice into all of the functions that I've written at this point, right? That the APIs don't change. Now, let's try to run some of this code here so we can see it. And again, you can do this on the Go playground, but I'm going to be running it locally with my new version of Go. And because it's not implemented yet, we're going to need to run the transpiler tool, go to go. And so I'm going to say go tool, go to go. Let's run the source code in this go to extension source code file. Now, when I do that, it's going to create a new Go file. It's going to run that, build it, and run it. And you can see here that I'm able to run those generic functions, and the output is identical from all the others. Now, the whole point here is being able to do something like this without having to write any more code, right? How nice would it be to say floats float 64, and we make a couple of, we make these values floats. There we go. And now I don't have a print floats function, and I don't want to write one. We can't use print assert because I don't have the special case statement for it. However, as I stated before, my reflect function is a generic function. It's using reflection to be able to handle this slice of floats. That should work. And now with the new generics, I should be able to just call my generic function passing in the floats slice, and it should also be able to display all those values, right? We can do it in 5 lines of code, or we can do it in these 8 lines of code, but they're both generic functions at the end of the day. And if I did everything right, there it is. We're seeing the code work without having to write any more implementation. Now, another thing I want to just share with you in terms of syntax is that this really is a parameter list using the square brackets, but just like this is a list of parameters, I mean, this is as well, which means that if I want to, I can explicitly specify to the compiler what T needs to be. I can do this, okay? I can pass in those list of types using the same square brackets, and everything still runs. We would call this explicitly providing the type information, but we don't really want to do that if we don't have to. We want to call functions no differently than we do today, and that's why it's important that the compiler is able to infer the type for T, which it is doing successfully in every one of these calls. I don't have to explicitly pass the type information here. The compiler is able to perform an implicit, or so let's say, call it an inferred. It's able to infer the type information based on what is being passed in. So in this case, it sees that a slice of integers was passed in. It knows the first parameter is based on T, therefore T must be an int, and everything just kind of flows. And one of the things I'm looking for when I write these generic functions as I'm learning is times when the type information can't be inferred, and that starts to act like a smell for me. And so there are these smells I'm trying to develop. Now, don't get me wrong, I've written some code where we have to be explicit with the type information, but for me, it's kind of a smell when I'm writing code in these generic functions where it can't be inferred. So I want you to look for that kind of stuff. And the few times it's happened to me here, the language team has corrected my implementation, and the inference was working again. Okay, awesome. Okay, so we've got through our first example here of a generic function. You've seen now that we need this type list to be able to tell the compiler that T is this generic type, that T is a type to be determined at compile time, that we are not going to be defining T at any moment in time. You also saw the call to the function and how we can do it explicitly in terms of passing the type information through, or better yet, we let the compiler infer that. And we really do realize now that with the reflect package, we can write generic functions in Go. The complexity of the code is greater, but we are able to do it. And for me, the big thing about generics, at least here, is I'm writing code as if I was working directly with a concrete type, since T will represent a concrete type at some point. Okay, brilliant. So we've got through this first example, all right, and we have a good understanding now of the current syntax. Let's continue on. Now, the generic functions are important, and we're going to definitely get back to them. But in any real world application, you've got to be able to define your own data types. And we want to be able to extend this concept of generics to the different types that we're going to need to define to solve the problem that we're working on. So let's look at generics in terms of user-defined or named types. And let's kind of walk through that same progression, okay? So on line 11, I've declared a new type. It's called vector int, and it's based on an underlying type of a slice of integers. And then on line 13, I implement a push method using what I call value semantic mutation, where we get our vector int, we get our own copy of vector int, we leverage append to add a value of type int into it, and then we return the new vector out. I mean, this is really the way append works, right? Gets a slice, gets a value, you get a new slice. It's the same really API design, or value semantic mutation. And this works. Now I have a vector that can work with just integers. Now, if I wanted a vector that can work with strings, here I am again, basically copying these same 4 lines of code, and all we're going to replace is ints out with string, and we're going to have to name this a little differently. And if I wanted to do this with floats, well, you already know what I'm going to say, Bill. I'll go ahead and type vector float, slice float, boom, there we go, and it's a simple copy and paste. Now, one of the things, though, that we're getting lucky about here, that the implementation is fairly simple here, is that append, which is a built-in function in Go, is a generic function. In fact, all of the built-in functions in Go are generic functions. They all can work with different types. Append can work with a slice of any type and a value of the same type and do that operation. So it's kind of interesting when you think about Go kind of already having the ability to do generics, whether it's with the reflect package or these built-in functions. Now, let's be fair. When it comes to the built-in function generic support, well, that's not extended to us, right? That's purely extended just to the language designers. So though these are generic functions, they're not done in a way that we can leverage the same, say, mechanics, right? All we have extended to us is that reflect package. But let's be clear, Go really does already have generics in the form of reflect and in the form of these built-in functions that come with the language. And it's the fact that this append function is generic that's really allowing me to write this code in the little amount of lines of code that I need. But we're back again that if I wanted this vector of float, I've got to copy and paste and make some quick changes. So we get back to the same question as before. Can I write a vector today, a single type vector today that can handle these ints and strings? And the answer is yes. Here we are again with our empty interface. The empty interface will allow us to write a single vector. If you can look at the push method here, it's identical. Again, look on line 20, look on line 34. It's really identical. The only thing that's changing is the type information, again, because append is already a generic function. But this vector that I'm defining on line 32 really has a different semantic, doesn't it? Because my vector int and string is bound to a single concrete type. We know that. If I iterate or work with the vector, I know what data I'm working with. See, that semantic is changing here because now if we're using the empty interface, well, we can store any type of data in this vector. We're not restricted to just int or string or float. And though the implementation in this particular case looks simplified compared to the concrete, the usability complexity now goes up because we need to know what concrete data we're pulling out, and there's no guarantee what it's going to be. I'm going to show you that. But here it is. We've got our empty interface vector. Now, what I think would be better here is defining a vector that can only work with a single type and do that in a generic way. And the draft for generics will give us the ability to do that. if you're noticing so far, the draft is really helping in these cases where we're needing to use the empty interface and potentially reflection or some form of like append generics in order to solve that problem. But here you can see that I could now use that same idea of type T. I'm going to get rid of this again so we see it. I like this initially when I'm looking at the code, so it just gives me clarity, right? Because what I'm really trying to say here on line 46 is I want to define a vector that is a slice of some type T to be determined at compile time. Now that I know that, I can put this back in and my brain kind of says, okay, now I know why the square brackets are there to reinforce the idea that T is to be determined at compile time and not necessarily a new type to be defined by me. Great. Now, if you look on line 48 and you look at the receiver, the square bracket T syntax carries over because we've got to tell the compiler here that the receiver value is going to be a vector generic of some type T, where T right there will also represent the value that we're passing in. So this all gets connected. The value that we pass in here will be the type of vector generic that we are going to be expecting to be using on the call. You see that, okay? So this type now is vector generic of some type T, and then we can leverage T here as the parameter. And again, we only need the single append call because it's a generic function that can work with a slice of any type or the value of the same type. Okay, brilliant. So we're seeing our first kind of user-defined generic type here where we need those square brackets one more time to tell the compiler that T is to be determined at compile time. Now, how do we construct this and work with it from a usability standpoint? Well, here are my concrete vector types, right? I can construct a vector int set to its 0 value thanks to var. I can then call push in this chain just to keep everything on one line. And we know that they can only be integers. And to kind of stress the idea of the concrete data, I want you to look at the print function here on line 59. Like, we're going to do our traditional for range. But because I know that the data in this vector is always going to be an integer, I can be very specific here with my format specifier and not have any issues. We know everything's always going to be a decimal, a %d. Now, when it comes to vector string, right, I know everything's going to be a string. I can use the %s format specifier here with no issues. The data is always of the same type. And this is where I want to stress some of the usability issues with using the empty interface here. Remember, I can interlace different data types in this particular vector. Now, you might look at that as a win, as an advantage, but eventually you need to get back to the concrete data. You're going to have a problem because now I'm back to doing type assertions to figure out what data I have to use the right specifier, and I don't even have a case for anything else. Right? I'm trying at this point not to rely on the reflective capabilities of print. And I just want to show you here that though the implementation of vector interface seemed, it was the same level as the other ones, the usability, because of the need to do type assertions, because you don't know what data is necessarily in any given position, adds a lot of complexity from usability point of view. So here's generics then. And what's nice here is that we still get to work with a single type vector. Now, notice the use of the square brackets again on the construction call. Remember that when we're making that function call, or in this case, the construction of the named type, we have the ability to pass the type information, but here we have no choice. There's nothing that the compiler can hang on to be able to infer the type here. So when it comes to the construction of these generic types, we're going to have to be explicit in this particular case and tell the compiler that I want a vector of integer values or a vector of string values. But what's nice is we get back to the more simplified version of knowing that we're only storing integers or strings. And as we range over this vector, we can get to our specifier. The type assertions have gone away, and we still have that generic goodness. Now, we can build and run this. Here we are. And all of it works. You see the interlacing on the empty interface, but we're back to having that strict type information for a vector. And once again, what's nice here is we could say, okay, float 64, good, we'll call that a float, right? We could change these variables out to floats right there. Maybe we'll just add some decimal points to bring that home. And maybe we'll say this is an F, this is an F. We know that this format specifier is an F, and we will change that. In other words, I'm not adding new code to handle floats as much as I'm just writing implementation now to start working with floats, right? And if I did everything right, we don't get any even runtime messages from the print function. We're using the right format specifier. We're now working with floats. So got the ability in this case to define this generic vector type where the underlying type can be of any type T to be determined at compile time. And we're doing that through the use of that explicit, call of int or float, using those square brackets again on the construction of our vector generic. Okay, brilliant. So we've seen one example now of defining a generic type and the construction of that there on line 82 and 89. And the complexity of these type assertions. And when I say complexity, again, I want to bring everybody and people, developers of all levels can understand a lot of this code fairly quickly. We start getting into type assertions and reflection, and the complexity kind of starts to exclude some people from that without having to spend more time learning, right? And we're trying to write code. We want to reduce bugs, and we want to reduce the amount of code that we need to write. We want to reduce bugs, and we want to make sure that the average developers on our team comprehend all of the code that's being written. And I'm trying to show you some cases here where I think generics can help to reduce complexity. But what about struct types and the use of pointers? Yep, that can get a little complex. So let's kind of share some of that. Now, what I'm doing here on line 14 and 20 is defining two struct types leveraging generics. This node is going to be a struct value that can store data of any given type T. Again, T to be determined at compile time. Every time you see this, I want you to think T to be determined at compile time, and this node can store some concrete data of type T. Now, since it's a linked list, this node will be able to point to the next node or the previous node. We're going to use our pointer semantics. And again, anytime I want to reference this struct type node, it's got to be node of some type T. It's not just a node, it's a node of some type T. And you'll see that syntax. Now, list contains the first and last pointers to our linked list. And so again, we're going to have a pointer to a node of some type T, a pointer to a node of some type T. And not only will generics in this first draft help to reduce some complexity around the empty interface, it's going to allow us to write these kind of container types, isn't it, right? Generic container types like these linked lists that I'm showing you. Now, I didn't fully implement our linked list here, but I did write an add method here. And you can see here that the receiver is a pointer receiver of type list of some type T. and it returns a pointer of type node of some type t, where we pass in a value of type t for the data we want to add. And you can see here as well, now that when we construct the node value, we construct it as a node of some type t. Because in this case, we don't explicitly know on line 26 what the type is. When we construct a node and a list, or let's say in this case, at least the list for the first time, we're going to have to be explicit about the type. But you can see in the implementation of this method that when we're constructing node, it's still node of some type t, right? We're being explicit. Remember when we had to pass in, hey, what is the type information? We had to be explicit for these user-defined types. We're kind of being explicit here, except we're saying that we're still really not sure what t is at this point. So construct a node of some type t, t to be determined at compile time. And so we now have this add method, right? Now I'm going to define a type named user, which is what we're going to store. And I want you to look here. Here is the initial construction of the list, where again, now we're not just going to say t, we're going to explicitly here say what t is, which is a user value. And now my add methods work with user values. Now, if you look here, I'm saying that t is a pointer to a user. That t is now a pointer type, which now means that add is expecting us to construct user values and provide the address of those user values. I want you to notice here that when we use t, we're allowing t to be a value or a pointer type. We're leaving that open to the developer. Now, if I go ahead and build this code, there we are. You can see the values and the address, the ampersand on the output. And we can see here that t was able to take the form of a value or a pointer. However, what if you wanted to restrict the data to just be pointer semantics? Well, you're not going to do anything here. Remember, the type list is a list of names of types to be determined at compile time. But if I did want to restrict t, or let's say the data, to just some pointer semantics, I could do this. And now what I'm really doing is saying that I want to store the data regardless of the type through our pointer semantics. I want to accept, regardless of the type, the data through those pointer semantics. I can do that. Now, the code I have won't compile anymore. We could take a look at the messaging. It's telling me I can't use this. I can't use this on 55. It's now seeing double indirection on line 60 and 61. So what I'm now having to do here is, let's get rid of this for a second. I still want to pass user for type t. I still want to define t as a user type, but we know now that we're going to be storing it as a pointer, and we're expecting it as a pointer. So now to make this code work, we come in and we satisfy the add method by using those addresses of user on the construction. But I'm not, in this case, having to say that this is a pointer. This would create that double indirection. And I'm locking the code in now to using those pointer semantics. So if you do things like this, right, we're going to specify a pointer of type t for the parameter list, or we're going to say this is a pointer of type t here, you are creating a restriction in the fact that everything's going to be pointer semantics, which might be a good thing. If we leave this open, right, you're now leaving it up to the caller to determine whether or not they want to use value or pointer semantics for the data that they're operating on. So it's something you need to think about when you're defining these generic types. Do you want to bind yourself immediately into pointer semantics, or do you want to leave it open for the user to decide what data semantic they need. And in most of these, in fact, all the examples you're going to see me working with, I'm going to be leaving that option open so we can write code like this and write code like that and use both semantics for these container types. Okay, so we now explored generic functions. We've explored user-defined types. We're at 8:15. I said I wanted to finish in 15 minutes. I'm going to try. I might go over 5 minutes here, so I apologize for that. Because there's some more aspects of the draft that we need to discuss. Now, we talked about functions, right, that are working with generic data types. And that's great. But there are going to be times where the implementation of a function is requiring some sort of constraint. Like we are expecting a method to exist for all values of type T. That's a constraint, right? And so we're going to have to find a way of telling the compiler that we have this constraint. Now, if you think about it, we kind of do this already, and I want to share that with you. But let's start here. So on line 13, I define a type named user, and I implement a method named string that returns a string. And what this method does is it creates a stringified version of user. I'm leveraging JSON, and this could have been anything, but it is a stringified version of user. On line 22, I define another type named customer, and I implement a method named string. And once again, I implement a stringified version of customer. Okay, great. Now, what if I wanted to be able to produce a stringified version of a collection of users or customers? Well, here we are. These are my concrete functions. You can see they take a slice of user, return a slice of string, take a slice of customer, return a slice of string. And essentially, these 5 lines of code are identical for both functions. Again, we're leveraging the generic append function to do this. We're using our traditional 4 ranges. And most importantly, we're leveraging the string behavior that we know exists off of user and customer to actually perform the heart of this work, which is the stringification of users and customers. So let's get back to kind of where we were before. Is it possible to write a more generic version of this in Go today? And I won't go through this in detail. We already did. But here we are again. Empty interface to accept the slices of any type, type assertions again, right? And different cases. So we already went down this use case, right? It's not a generic function. If I want to use more entities, I've got to write more case statements. So, but we're close. Now, can we use reflection? Well, we absolutely can. There it is. But we just went from 5 lines of code to about 13 lines of code. And again, the Go developers from all levels cannot just come in and start to consume this code. I mean, it took me probably 15 minutes to write this code, and I've been working in Go for 7 years, and I had to look at the reflect package, and I have some experience there. But if you look at this, this truly is a generic version of our stringify function, right? We can accept a slice of any type. We can validate that it's a slice. Maybe we're changing the semantics a little bit here with the nil, even if there was data there, but okay. We can construct a slice of strings. We can't use our 4 range, but we can iterate over I. We saw that we can iterate over every element in the slice. And here's something new. Because we have to call the string method, I can ask if there is a method named string. Now, I got to do an extra check, because if there isn't, well, we're done. But then I can call that string method and then append that value to the slice. So I can do everything that I did before, except I get no compile time checks here. Everything's at runtime. And I do have the potential of somebody calling this stringify function with something other than a slice, or with a slice of values that don't implement the string method. We're not going to get that compiler check. But there it is. It's a generic function nonetheless. But we went from 5 lines of code to about 13, and this is a lot more complex. Okay, so the question is, can we do it with our generics? And we absolutely can. And I'm going to break this down again, because I find it's easier to understand when we do. Okay, so what am I trying to do again? I'm trying to write a generic stringify function that works with a slice of some type t to be determined at compile time. And then I can use the same 5 lines of code that I used before with my concrete implementation, since t will represent a concrete type. I'm back to this make, I'm back to the for range, and I'm back to being able to call string. Well, we got a couple of issues. First, as we already know, I've got to add this in because t is to be determined at compile time, and that's the only way to let the compiler know not to expect us to define t. The problem here is that I have a constraint in the implementation of this function. This function expects that for whatever value that we use for t, that a string method exists. We have to apply the constraint. Now, I want you to think about this first before we go on. We leverage constraints like this quite a bit in Go. Look, can't I write a function named Bill, which uses the stringer interface from the fump package as the type for the data that we want to pass in, right? This isn't a concrete function, right? This is a polymorphic function, right? Bill is saying that I will accept a piece of concrete data, any value or pointer, that implements the stringer interface. It's asking for data not based on what it is, but based on what it can do, the constraint being what it can do, and the constraint coming from the stringer interface, which says that the data must have a method named string that returns a string. If you haven't realized yet, my methods that I implemented for user and for customer are satisfying the fumped.stringer interface. This is what that interface has as part of its method set. So this polymorphic function is leveraging the interface to define a constraint that the only concrete data that can be passed into Bill is data that exhibits this string behavior. So we're using interfaces already today to define behavioral constraints on data that can be passed to our polymorphic functions. And I have the same kind of issue here. We have to make sure, we have to define the constraint that t can only be of a type where the data will have a method named string. And so the current idea in the draft is to leverage the same interface mechanics that we do today in our traditional polymorphic functions. And so if I apply fumped.stringer just after the identifier t in this type list, what I'm doing is essentially the same thing. I'm telling the compiler that t must be constrained to just types whose values will implement or contain or exhibit this string behavior. And this is how we're going to apply constraint when there needs to be constraint because of the implementation details of those generic functions. Now, if we go to main real quick, you can see that I'm constructing a slice of users and a slice of customers, and I'm passing that slice to all 4 functions that I've written. If I go back over to the terminal and we come back in here, I can run that, and you can see the stringified version of users and customers. Now, I'm not going to create another slice here. That would, be redundant. But watch what happens if I remove the constraint. Very similar to what would happen if we didn't define the right constraint for our polymorphic functions. You can see here the compiler is complaining because you're trying to call a method named string, and that's undefined because it's not bound for type T. It's really the same messaging we get for our traditional polymorphic functions, except kind of on this side, we're saying, hey, you're binding some generic type T, and guess what? You're not saying that T has to have this method, so we've got a problem. So it's kind of reversed in the sense that in our traditional polymorphic functions, we're explicitly saying there, hey, I need this to have T, and then we say, well, the data does or doesn't. In this case, what we're now saying is, well, type T has to have this behavior, and it does or it doesn't. And because the compiler sees the method call for values of type T, it now says, hey, Bill, you're not saying that this has to happen, so let's apply the constraint. So here we are. So now what we see is the ability to restrict what type T can be based on behavior that we know must exist for those values that will be used for type T. Okay, awesome. So we're seeing the use of the interface, again, the reuse of the interface in a very similar way from our polymorphic functions. I love that. I love that, right? But. Whew. There is another type of constraint that we have to think about. And it's not necessarily behavioral constraint. I would argue it's more a constraint on the property of the data. Now, let me show you an example of what I mean. And I want you to really just kind of focus on line 16, if you would, please. And again, I'm going to remove this for a second. On line 16, what am I trying to do? I'm trying to create a generic function named add, which can take two values of type T, add them together to return a new value of type T, right? The idea here is I want to apply the plus operator. Now, let's get back to the understanding that we have to say that T is a type to be determined at compile time. So now I lay that in. Beautiful. And most likely, this is how not most likely, this is kind of how I work when I start writing these generic functions. And the more comfortable I get, I feel more comfortable putting in those square brackets. But in the very beginning, I think it adds some value to be able to say, okay, I know we're going to have this type T. Now let's determine that type T is a generic type. But I have a problem. You see, not all data can be used with the plus operator, right? Our struct types, user and customer, from the previous example, can't be used in this kind of expression. And since we're not an object-oriented programming language, and we don't have operator overloading, I can't write an operator plus method. I mean, the user and the customer will never work. So there is a constraint in that T can't be all different types of data, but only data that can work with this plus operator. It's now not so much behavior as what that data, the properties of the data provide. So how do we define a constraint where we can make sure the data and all data that we can potentially pass will work with the plus operator? Well, in the current draft, this is the current idea. And the idea is to leverage the interface again and to define an interface that would have a type list. In this case, what I'm saying is that the add-only interface is creating a constraint where the data can only be of this type or the underlying data for the type, okay? In this case, Bill would comply because the underlying type is a string and string is in this list. I want to specify that this type list is not just the type itself. I could say Bill, But if Bill has an underlying type of string, Bill would satisfy the interface, okay? But what we're saying here is that this is the only type of data that satisfies the interface. And now I can apply the constraint to add and now have the guarantee that the plus operator works with all values of type T that are allowed through this constraint to be passed in. And this is the current idea for being able to provide constraints around these types of operations. Now, I will tell you this. This arguably starts to move us away a little bit maybe from Go. It kind of starts to break things because at least in the current draft, I'm no longer able to use this interface when writing a traditional polymorphic function. If I tried to do this right now, the compiler will complain. And you know, Go is very much not like this. Go doesn't really have scenarios where an interface can work sometimes and then sometimes it can't. And the language team really is the one who brought this up to me. They don't necessarily like this. They're looking for some new or different ways to apply this type of constraint for generic functions where it's currently not working for our traditional polymorphic functions. Now, one solution could be to allow this to work with our traditional polymorphic functions, to say that Bill will only work with data based on this set. But you know, remember when I was talking about our polymorphic functions, I said a polymorphic function is a function that asks for data not based on what it is, but based on what it can do. So that kind of breaks that, right? Because here we're saying that we're only going to work with data based on what it is. And that's not very polymorphic in that case, right? So the fact that it breaks these polymorphic functions is, right? Everybody's not necessarily happy with that. Now, I'm going to show you a little bit more code that maybe solves this problem, but this is a part of the draft that the language team would love some feedback on, and again, some maybe different ideas on how to apply this type of constraint in this type of scenario. But let me show you a couple more things here. One idea is to define a set of pre-declared constraints, like comparable is one of them that's currently implemented in the draft. If you look at the implementation of this code, we have the comparable here, right? If v equates to find, right? The double equal sign. And again, not all types can be used here. Our struct types can, but our slices can't. So if you happen to pass a slice of some type for t, well, that's not going to work here. So again, we have to constrain the generic function to just data that's comparable. And one idea here is to have some pre-declared type constraints that we don't have to worry about defining ourselves. Interesting, right? And then the last thing I want to show you here is I'm going to define a type called person and food. I'm going to write a method named match. All match does is match the name of the receiver to the value being passed in and returns true or false. And the idea is this match function. Now, let's go back through everything one more time. I want to write a generic function named match, which takes a slice of some type t and a value of that same type t. I can range over this list, and then for each value in the list, call match against the value that I want to find. So we know that t is a generic type. Great. We also know that we're expecting t to have behavior like match, which now means we need an interface that we're going to call matcher. Now, let's take a look at the matcher interface. And I want to get rid of this for a second. I don't want that to interfere for a second. Look at the matcher interface. At this point, when we declare the match behavior, we have to be able to declare it to accept a value of type t to be determined at compile time. And so you see the use of the square brackets on the interface declaration to tell the compiler that match will work with a value of type T to be determined at compile time. And so you see here how that generic type can extend all the way into the interface, because those methods that we're defining might require to be declared as a generic method in this case. Now, the other thing that I pulled out was the type list. And I'm showing you this because there is no restriction in defining an interface that has both behavior and a type list. Now, I will tell you that there is no need for this type list. The constraint that we really have here is on behavior. And I'm only doing this to show you that this code can compile and run. But I have struggled, when I say struggled, I have struggled to find a practical reason to have both a type list and behavior. I have not found a reason or any practical example where the implementation of this function would require behavior and then some form of operators like plus or equals, where we're also applying that to type T. If you had a combination where you were calling the behavior and you were doing something like v plus find, right? And I can't find a practical reason to do this. But if you were doing something like this, now you would need to make sure that you had two types of constraints, behavior and that kind of property constraint, where now you might have the type list or you might use comparable. I just haven't found one yet. And it doesn't mean that it doesn't exist. But if we find a year from now that there is no real practical implementation of a generic function that requires both, then maybe we don't need this. And then maybe the solution ends up being that we don't have to put these type lists in interfaces, and we can do that in a different way where the constraint is either behavioral or type list, where it doesn't have to be both. We don't know enough yet. I can tell you that. And it's going to require a lot more people looking at code that they have today in production or their personal projects and finding real practical needs. And that's the thing here on the draft that I want to stress, that the language team is at some level right now guessing what is a practical need and what isn't, okay? And they can't see the future. And that's why they need everybody involved, because you might discover a practical need for something for this first release that's been omitted that now says, yeah, we got to add that. Or we might find that in this case, there's really never a need to have an interface that has both a type list and behavior. And if that ends up being the case, then that could simplify some of the other issues we have with now breaking interfaces to be used in our traditional polymorphic ways. The point is that unless we're all working with this new syntax and looking at our programs and looking at ways where generics can reduce the complexity, this is so important, reduce the complexity, increase the readability, and then therefore reduce bugs and allow more people on our teams the ability to read and maintain this code, then maybe we don't need it. Maybe we don't need it, or we're potentially missing something. Now it's 8:38. I'm way beyond my time here, so I am going to end with this. We didn't get to number 7. I apologize. The only thing I'm going to share with you on number 6 is that the type list can be of multiple identifiers. Okay, so I've been just using one. You can have many. Also, you don't have to just have single letter names, okay? You can use Let's just make it singular. You can use full names. It doesn't even have to be uppercase or lowercase here. We are, as a community, trying to figure out what are the best guidelines. I'll talk about that in a second. But when it comes to these kind of list types, these collections, I tend to like to use the single letters more. Now, if you noticed, I had a constraint here because V is expecting the string behavior. The only other thing I want to share with you is that once a type in this list has a constraint, they all need a constraint. And so you're seeing me use the empty interface here because I have to apply a constraint where I really don't want one. And the empty interface is a constraint that constrains nothing, if you think about it, right? So that's what you're seeing here. If you ever see the empty interface being listed in a type list, it should only be because another type in this list needed a proper constraint. All right, I don't have time to go through number 7, which really wants to focus around the idea of zero value returns for your generic type. I'm going to leave that up to you to look at. It's not critical that we look at that right there. So with that being said, I'm kind of back here. I want to just say a couple more things, and then I'm going to open it up to questions. One of the things I've asked the language team to do before this ever gets released is to provide really nice documentation on idioms, guidelines, and a lot of practical example code that we could all leverage when we're writing code for our applications. And I'm really pushing the language team to do that, and I hope to be a part of that process. Some of what I'm doing here is the initial beginnings of trying to figure out good practical examples with good practical guidelines and idioms to follow. So I really do hope that everybody goes through the rest of this code and then explores their projects and looks to see if any of this first version of generics can make any of their code cleaner, more readable, more maintainable. This is what we're going to go after, right? Don't focus on this for performance because, again, we don't know how this is ultimately going to be implemented underneath. There are trade-offs to make in terms of binary size, in terms of performance, in terms of lots of things. So let's not think about this in terms of performance. We're going to think about this in terms of readability and usability. Okay, with all that being said, I am open to questions. So not sure how I will see those, but my hosts I think, can pop something up in front of me.
Right. Thank you, Bill. Yeah, it was very informative. There are a few questions. I think you addressed the performance part. I think we'll skip that question. There is a question by Nicole around 7:52. I'm hoping Stanley can bring up for you. The question is this. Can you see it?
I don't see any questions. So should I? Oh, I can only see it if I go back into this
StreamYard, yes.
This view. You want me back here? If I stop sharing, oh, perfect. I don't have to share. Beautiful. Okay, love it. We're not explicitly specifying the type for T. Does it infer the type on compile time, and do we still keep the type safety within the function? Yes, we're going to keep that type safety because we're going to be bound to that concrete type at compile time. And the inference is really more of a usability aspect where we don't have to, declare something that we know the compiler can. So at the end of the day, what I want you to think about, at least the way I think about it, is your generic function is a concrete implementation of that code. And you can think in terms of that concrete type. You can write the code in terms of the concrete type. right? This isn't a traditional polymorphic function, right? This is, we can call it maybe compile time polymorphism. And so you're going to have that strong type safety at the compile time, and you get to work with the concrete type. So hopefully that answers your question, Nico. Now, again, I don't know how this is eventually going to get implemented, Nico, okay? They could choose to write an individual implementation for all types that will be bound to T, or they could decide to leverage generics underneath like they do with append and make, and still just have one function for everything, right? At least say for that generic function. So we don't know exactly what's going to happen yet under the covers, but at least at compile time, you're going to get that type safetiness you would get with any concrete type.
Okay. Right, there's some new comments. Maybe you go to the next question. I'll bring up the one on again by Nico. I'm not sure whether this is similar. Maybe.
We're not explicitly specifying the type for T, and we want to do something with T. Do we still need to rely on type assertions? When we're working with generics, there will be no use for type assertions. The type assertions only apply to interface. Concrete type stored inside of interfaces. That's the only time you're going to use a type assertion. That's where that mechanic is. The whole point of the generic function or these types is so we don't have to leverage the type assertions. We know we're working with a value of int, string, user, whatever it is.
Yep, from Mark.
Curious question, in what kind of situations do you find yourself reaching out for generics? Excellent question. This version of generics is going to be very good in several areas of the language. One, the reduction of the use of the empty interface. So anywhere in your code today, you're using the empty interface because you had to do something more generic. That's probably a good place. Now, again, when it comes to unmarshalling, decoding, and encode, I think reflection's still going to be the right tool there. But I have functions in some projects that are using the empty interface as a return because we're trying to do something more generic. So I think you want to look for empty interface implementations. Container types. So if you're building those linked lists, those hashes, those queues, certain things like that, maps, right? Where, again, you're probably using the empty interface. We can now have a concrete implementation of that. Areas of the standard library that I'm very excited about. One is I think we could potentially see a concurrency package. We can create channels of a generic type. I've got one example of that. And I think there is, I'm reaching because I haven't done the research, but I imagine there are lots of bugs and extra levels of complexity around concurrency in Go software today, because so many of us have to write those patterns ourselves. How many of us have written our own fan outs and fan ins and pools and all of these things, right? And we all do it a little differently. And the thing is that if we could standardize just the concurrency code and get it into the standard library, I think that could reduce a lot of bugs. I think it could reduce a lot of complexity and gives us standards around that. So I think generics can come in and help us define some of those standard library packages. There's other packages there too, like the sync package, where we've got a map and a pool type that has to use the empty interface. That would be nice to have concrete types there. We could avoid the, definitely avoid the use of type assertions there. And I wonder if the context package, its value bag, could potentially be better served with a concrete type. I don't know, right? These are some of those are thought experiments. So I think what you want to look at in your code is empty interface, places where you're using the empty interface, places where maybe you've created some sort of container types, like things that I've shown you. And then the one example I didn't get to, because it would have taken another 15 minutes, and we just don't have the time, which is example number 7. It's kind of an interesting example of different way that you could leverage, say, polymorphism in Go. The compiler, this draft will allow you, thanks to that type list, to see a common set of fields. And so there's some ideas I have where we can reduce the need for methods when we know in a generic function that all types have a field like ID. So there's some interesting things there. Definitely look at that example number 7. And it could give you some other ideas.
Okay, maybe we have a last question. Let's bring up Michael's. Yeah.
Okay, at this point, outside of my repo, outside of the draft document, because the draft document is showing a lot of code, and outside of my repo, which is becoming a collection of interesting code that I'm writing, but others are writing. I don't know. I know that I've seen maybe a handful of blog posts out there, but I honestly don't know where else you can see examples. If you want to contribute an example, send me an email. We'll put my email in there. I will take any examples you have. I'll look at them. I'll work with you on them. And if I think it's unique and something that we should teach to or share in one way or the other, I will add it to the repo for sure. So please send me any examples you have. Remember, I may have to refactor them down a little bit, but I'd love all of that. So send that to me. And other than that, just look for blog posts as they come out or read the draft document for other examples.
Okay. Really, the last question, I think, is again from Nico. I think this is the interesting one.
Yeah. So this is the big question, Nico. This is the question, right? And this is going to take a community to make sure. This isn't, look, when everybody comes to Go for the first time, look at just about everybody's first year of Go code. And what will you see? In most cases, an abuse of channels. People want to play with the channels so bad that they're using them everywhere, even if they don't need them. So let's be real. When this comes out, people are going to use this in places that they probably don't need to. So how do we maintain the simplicity of the code we're writing when generics comes in? It turns into a community effort where, one, code that's being published in open source, code that's being published in blogs, we need to nicely and politely and with the right discourse explain that maybe we shouldn't be using generics there and use that as a teaching moment. At work, when people on your team want to apply generics somewhere and it really is making things more complicated, again, with the same politeness and positivity, try to explain that, hey, this isn't where it needs to be. See, the way I work is I'll write concrete implementations of code first. Then I'll ask the question, does this code need to be decoupled? And then the question is, okay, if it needs to be decoupled, then what interfaces do we need to define, right? We're going to go with that traditional polymorphic function. To me, generics should be the third choice. When your current polymorphic functions, traditional polymorphic functions don't work, then we can consider generics. But this is a teaching. And this is why I've asked the language team to please, before this gets released, to focus on idioms, guidelines, and lots of example code to help reduce this potential problem we might have with a lot of code out there starting to get more complex. But it's going to take a community, Nico. There's no pixie dust on this one. We've got to do it together.
Okay. Okay. We have time for one last one. This is probably Chunkit. Let's take the last one and then we call it a day.
I don't know enough to answer that question. Actually, I don't know way enough to answer that question. But if you send me that question in an email, I'll send it over to the language team, and I'll get them to. I'll ask them to provide an answer when they have time. Is that fair? So send that to me in an email. I'll send it over to the language team, and I know they're really, really busy, but they are really, really interested in these types of questions and everything that you have to say. So those 3 links that I provided, hopefully everybody has access to them. This survey link is your opportunity to share these thoughts and ideas with the language team. Trust me, they see these results and they're looking at them, and they're helping to also form understanding on what they need to focus on as well. So, and it's an anonymous survey, so you can feel very much free to share what you want there. If you're not comfortable sharing stuff on the mailing list or in GitHub issues, then this is that opportunity. And you can always send me an email with questions, and if I can't answer them, I'll ask them and we'll get answers as well. I cannot stress again enough how much the Go language team wants to hear from you. They want this to be successful, and they know it can't be successful without your help.
Okay, thank you, Bill, and thank you for the community of staying put. And it's a very interesting talk. So let's not hold back the night and the morning for everyone. Right? Thank you very much again, Bill, and thank you, Chris. You're still on the line on sharing your thoughts. Right. Until August, we will see you again. Thank you all, and bye-bye.